All right, let's get right into it. From the physical cables plugged into the wall to all the cloud services we use every single day, our digital world is just built on this incredibly complex web of networks. So in this explainer, we're going to break it all down and demystify how it all fits together, right from the ground up. And hey, this is not going to be some dry technical manual. The goal here is to find those aha moments, the practical stuff that shows you not just how all this tech works, but, and this is the important part, why it works the way it does and why it matters right now. So here's our roadmap. We're going to start with the actual physical boxes and wires. Then we'll get into the digital language that they all speak. From there, we'll zoom out to see how whole networks connect across the globe, how we keep them safe and secure, and finally, we'll look at how it's all becoming way smarter and more automated. Let's do it. Okay, first things first. Everything, and I mean absolutely everything, in our digital world starts with physical hardware. You've got to have boxes and wires. These are the unsung heroes that are actually moving our data from point A to point B. To really get this, think about it like this. An old network hub was basically like a room where everyone is shouting at the same time. It's total chaos, super inefficient. A modern switch, on the other hand, is so much smarter. It's like a traffic cop, directing every single piece of data exactly where it needs to go in its own private lane. That shift from a shouting match to private conversations was a massive, massive leap forward for networking. So that brings up a really good question. I mean, we've been using copper cables for over 100 years, and for a lot of things, they still work just fine. So why on earth are we spending billions of dollars laying all of this advanced fiber optic cable across the entire planet? Well, the answer really boils down to three huge advantages: speed, distance, and immunity. Fiber can carry way, way more data. It can send that signal for miles and miles without it getting weaker. And this is a big one, unlike copper, it is completely immune to electrical interference. These three things make it the undisputed backbone of the modern internet. Okay, so we've got the hardware in place. Now what? How do all these devices actually talk to each other? Well, they need a shared language, right? A set of rules, or protocols, that basically govern the entire conversation. And this is where you hit a really crucial trade-off. Think of TCP like certified mail. It's a bit slower, because it needs all these receipts and confirmations, but you are guaranteed that it gets there. UDP, on the other hand, is like dropping a postcard in the mail. It's incredibly fast, super low effort, but there's no guarantee it'll arrive. You would never use a postcard to send banking information, right? But it's absolutely perfect for a live video stream where speed is everything, and losing a single pixel doesn't really matter. You ever wonder how your phone just magically gets online the second you connect to a new Wi-Fi network? It's all thanks to this lightning-fast four-step dance called DORA. Your device basically shouts out, "Hey, I need an address." A server says, "Here's one you can use." Your device goes, "Awesome, I'll take it." And the server confirms, "Cool, it's all yours." And all of this happens in the blink of an eye. And how is it that you can be on a video call, browsing the web, and downloading emails all at the same time? It's actually a pretty simple, elegant system. The IP address is like the street address for a big apartment building. It gets all the data to your computer. But the port number, that's the specific apartment number. It makes sure the email data goes to your email app, the web data goes to your browser, and the video call data goes to its application. Simple as that. All right, now let's zoom out a bit. We've seen how devices talk on one network, but how do we go from that to the massive interconnected system that we call the internet? This is where things get really, really powerful. VLANs are an absolutely fundamental tool for organization and for security. Basically, they let you take one single physical switch and digitally slice it up into multiple totally separate networks. It's like putting up invisible walls inside the switch that keep different groups of devices from talking to each other directly. And why would you want to do that? Well, for two big reasons: organization and security. You can put all of the marketing team's computers on their own VLAN, even if they're sitting on totally different floors of the building. And, this is crucial, for anyone on the marketing VLAN to talk to the sales VLAN, that traffic has to go through a router, and that router acts as a security checkpoint where you can enforce all sorts of rules. So, how do these routers know where to send all this data? They need a map. With static routing, an administrator literally gives the router a fixed, hand-drawn map. It's simple, sure, but if a road closes down, that map is suddenly useless. Dynamic routing is way better. It's like a live GPS network. The routers are constantly talking to each other, automatically figuring out the best path, and if there's an outage, They adapt instantly. And modern protocols like OSPF are incredibly smart. They don't just find the path with the fewest turns or hops. No, they build a map of the entire network and find the truly fastest route based on bandwidth. It's always going to pick the 3-lane highway over a short but slow country road.
Okay, so we've built this amazing globe-spanning network. Awesome. Now we have to protect it. We have to set up some rules of the road to control who can go where and what they're allowed to do when they get there.
Access control lists are our digital security guards. A standard ACL is like a bouncer at a club. It just checks your ID, your source IP, and asks, are you on the list? That's it. An extended ACL, though, is like a full security detail. It's going to ask, who are you, where are you going, and what exactly is your business there? It checks every single detail before it lets you pass. It's just way, way more powerful.
And here is the single most important thing to remember about these lists. It's a principle called default deny. At the very bottom of every single list, there's this invisible rule that just says, deny everything else. This means if you haven't explicitly, specifically permitted some traffic, it gets dropped. Period.
So riddle me this. How can your internet provider give you just one public IP address, but you can have your laptop, your phone, your smart TV, your gaming console all online at the exact same time? The answer is this little bit of magic called network address translation. Your router lets all of those devices share that one single address, and it just uses different port numbers to keep every single conversation straight. It's genius.
But what happens if that one router connecting your whole office to the internet just fails? Well, everyone's offline. That's a single point of failure. The solution is redundancy with something like HSRP. You have two routers working as a team. One is active, handling all the traffic. The other is on standby, just watching. The second the active one has a problem, the standby router takes over instantly, and nobody on the network even notices a thing.
All right, finally, let's look at where things are going. The whole era of manually logging into every single device to configure it is fading away. We're moving to a totally new model, networks that are intelligent, programmable, and driven by code. Software-defined networking, or SDN, is a completely revolutionary idea. See, for decades, every router and switch had its own little brain inside. SDN basically rips all those individual brains out and puts them into one central, super powerful software controller. This controller gets this God's eye view of the entire network, and it can program all the hardware on the fly, making the whole system incredibly fast and agile.
And these new automated networks are programmed with powerful tools like the ones you see here. The biggest difference between them is how they work. Ansible is agentless, which means it actively pushes changes out to devices. Puppet and Chef, on the other hand, are agent-based. They use a little piece of software on each device that periodically checks in with a master server to pull down any new instructions.
And this all brings us to a final, really crucial question. We've gone all the way from simple hubs to these intelligent, automated systems. So as networks keep getting more complex and security threats get more and more sophisticated, the skills we all need to manage them have to evolve too. The real question for anyone in this field is, how will you adapt, and what's coming next?